Hello, everyone. Welcome. My name is Dava Newman. I'm the Apollo Program Professor at MIT and the Director of the Media Lab, and it is my great honor to welcome you to our Human Exploration panel. Exploration is not just back, it is thriving. And we're going to have an incredible discussion about space exploration, but for humanity, thinking about why is this such an exciting time, and the big questions, literally the very big questions. When will we find life elsewhere? How does space benefit Earth? So it's my great honor to introduce our panelists. We have Josef Aschbacher, the ESA, European Space Agency General Director. And we have astronaut Matthias Maurer, who's going to talk to us about the personal experience of living off-planet. He's just recently returned from 6 months on the International Space Station. So to cue up the space, looking, how does space, I say in the solar system, we're exploring, again, how does it really change and move human hearts? Exploring, will we find life elsewhere? And then the science, the hundreds of science missions that we have active for all of us, and the democratization of space and human space flight is thriving. We're gonna have a large 10 minutes for questions and answers, so after you hear the panelists, please queue up your questions and we'll invite you to ask your own questions. We're live, and so look forward to the two panelists. Josef, please.
So thank you, Dava, and very welcome also from my side. Very happy to show a couple of slides and say where we are in exploration. And really, we are back in exploration, but back on the front lines of the newspapers because so much has happened recently. This is one of the pictures which I'm sure you have seen in some of the newspapers or news channels, the Pillars of Creation, James Webb Space Telescope, which we launched on Christmas Day last year as a cooperation between NASA, the European Space Agency, and the Canadian Space Agency. And I think it really shows that, first of all, space is international. We cooperate among the major space agencies, but also we do incredible things. If you create images like this, as they have been created from the James Webb Space Telescope, they really are so stunning because they are looking, or the James Webb Space Telescope is looking back into the very origins of the universe. As you know, the universe is a bit more than 14 billion years old, and we go as close as possible to the Big Bang, about 300 million years after the Big Bang, and this is as close as we can get to really explore, see the creation of the universe or how it looked like in the very early days, and therefore better understand, of course, where we come from and what this is all about. We have a couple of slides to go through and then really would like to stimulate the discussion. I will share them with Matthias. But before I hand over to him, just to recall that space is really used everywhere. Of course, we see the fascinating images of the James Webb Space Telescope and all the exploration we do there, which is really quite amazing. But also down on planet Earth, space is used every single day. What you see here are two images of the UK, France, or parts of France in 2 years, July 21 and July 22. And I think the images already says it all. 1 year we had a very strong drought, which was last summer, which has turned all the green landscape into brown soil. And this is just showing, I mean, this is something that, of course, you experience on the ground. We had a heat wave with maximum temperatures in most parts of Europe. And this is just proof how you use satellites on a daily level to monitor what happens, but also to predict, especially for agriculture and many other applications. And this is just one of the many examples which shows the power of space, that you can, of course, do this on any single point on our planet. Maybe just one small remark on these images. They are produced with Sentinel-2, which is one of the satellites of the Copernicus program, a program which we develop as from the European Space Agencies together with the European Commission. And all the data which we are producing are for free to anyone in the world. So if you want to log on to the website, you can download your image of yesterday, of your home garden, of your next ski trip or whatever you have in mind. They are for free, and you can download them from any part in the world and at any time. We disseminate about 350 terabytes of data every single day through these channels. This is space exploration, and this is exactly where Matthias comes to play, but I will hand over to him in 1 minute. This is showing the exploration program which we have just presented to our ministers at European Space Agency's Ministerial Council, where we ask every 3 years for funding by our member states of our activities. And I have to say we got a record budget from our ministers, 17% higher than the previous ministerial, plus inflation that comes on top. So this, at these times, under these circumstances of the economy and the state in the world is quite remarkable, showing also that the ministers are recognizing space as a strategic activity where you really need to invest and really need to sign up to programs. So we have programs going to the space station, of course, with the European Space Agency, cooperating with the NASA and the other space agency partners of the ISS. We have programs going to the moon and going to Mars. Some rover missions, Mars Sample Return and ExoMars in particular. But on the moon, we have quite a number of activities within the Artemis program, but also our own missions to the moon. One is called Argonaut, which transports about 1.5 tons of mass to the moon surface, and also have Moonlight, which is a navigation communication system around the moon, so you can make phone calls and navigate on the moon once there's infrastructure established. Maybe at this point I hand over to Matthias, who goes a bit through the exploration part, and then I come back again. Matthias.
Thank you. Good morning, everyone. So here we see on the slide the 3 destinations where we want to send humans to. The first destination is low Earth orbit. We have the International Space Station. It's not the only station that we have currently in space. We also have the Chinese space station, and in the future we will also see commercial space stations. We use low Earth orbit to perform experiments, to do science in zero gravity. There we can do stuff that we cannot do on our planet Earth, to understand better how systems work, but also to develop new materials, to learn about humans being in such extreme conditions, and to try what we can learn and benefit and bring back to improve the healing or like the medicine on Earth. So we will continue also flying to low Earth orbit because it's a wonderful destination, and it's also of an economic benefit because in the future we also hope to start some early manufacturing there. The next destination is the moon, and flying to the moon, it's 1,000 times further than the ISS. So ISS flies in 400 kilometers altitude, the moon is 400,000 kilometers altitude, so it's further away. It's also more challenging because before we can land there, we need to get there, so we need more powerful rockets. You need better technology. And before we land there, we also are planning to install a new space station that is flying around the moon. It's called a Deep Space Gateway. And on the Deep Space Gateway, we want to use this platform also to learn how we can later on travel to the third destination, which is Mars. Flying to Mars, it's in theory possible today with the technology that we have, but then we would go there, we would fill up all our rocket with food and water and supplies for our astronauts and fuel for the return trip, and then there wouldn't be any room left for experiments. So we would go there, plant the flag and come back. That's not the purpose, what we want to do. So our idea is we want to go there and only take along what we need, and then arrive there and find everything what we need to stay there, to build a station, and also to come back later on with the resources that we get there. And that requires that we learn all this technology, and we can learn only this by going first to the moon, mature it. If it goes wrong, if the technology fails, we're back in a few days on planet Earth. You cannot come back quickly from planet Mars. I start with the very first destination, which is the ISS. So here's a photo of me last year in Cupola. It's our favorite place on the ISS, the window. We observe planet Earth. And well, it's usually what we do in our spare time, but we also use this place whenever a supply ship comes, because we need to catch it with the robotic arm. From there, we also look down to planet Earth, and people ask us, can you see climate change? And I can say, like, climate change takes place over a long duration of time, but I can see indications that help me to understand what's happening down there. So you look down, you see planet Earth is absolutely blue, and in the background it's all black. It's the darkness of space. But when you fly over planet Earth, There are green areas, dark green areas, which is the rainforest. And right next to it, there's a light green area, which is the agricultural area. And somehow there are very, very many fires exactly on the border between the dark green and the light green. And that's when you understand people are burning down the rainforest to create more room for agriculture. And then you fly further on and you see like desert areas. And you think like, shouldn't there be a lake here? In my old maps, there's a lake, the Arrow Lake, and it's gone. You don't see anything. So that's what we as astronauts can observe from space. We understand there is a climate change, but obviously the satellite data provides way more insight. That was the most exciting day for me in space, stepping outside of the spacecraft, stepping into the unknown, repairing something on the outside, but also installing new stuff. And to do this, we need space hardware. And this space hardware we need to improve in order to enable us also for the future to explore the moon. And maybe you can say a few words because you're the expert on this technology.
Oh, thank you. Well, EVA, or extravehicular activity, so think about it as taking the entire spacecraft, all the systems, and shrinking it around the human body. So I think it's an engineering feat, but the disadvantage is you're in a pressurized balloon, a pressurized shell, so the astronauts really have to work against the suit. So advanced technology hopefully will go with human performance. We're getting to the moon, we're gonna go on Mars, we're going there to explore, to find the evidence of past life or life. So we really need to make the astronauts very, very mobile. So that's where future technologies come in. We're protecting them, we're keeping them alive, keeping them safe, but it's quite a feat, an engineering feat, because you have to provide oxygen, scrub the carbon dioxide, make sure that they're safe and comfortable. So it's the miniaturization of the spacecraft, if you will, and then empowering the astronauts in human performance.
Yeah, just to give you an example, we're here in Davos. You see all the mountains on the outside. On the moon, we want to climb down a crater, which is, I believe, 2 kilometers deep. It's very steep. So imagine this suit and climbing down the hills here on Davos, you wouldn't have any chance. So that's why we need better technology to enable us space exploration. And this is the beginning of the new exploration era. It's the Artemis 1 launch. So it's a moon rocket that was launched last year, and NASA is leading the field, but Europe is being part of this because we provide essential elements to this mission. We here see the Orion capsule, which will bring astronauts to the surface of the moon, or to the orbit of the moon, I should say, and from there we descend. And this capsule is driven by European technology. And that's what we hopefully will see in the future. My dream is also to be in that capsule. I landed already in the water exactly like this last year in May, but that was coming down from the ISS. And from the ISS, you don't have the speed that you have when you come back from the moon. And I hand back to Josef now.
Oh, thank you. I think this really shows the fascination of spaceflight. And let me just say also that this is, of course, NASA is in the lead, as Matthias was saying, but as the head of the European Space Agency, I'm very proud that we also contribute to this mission, and we are one of the partners of this international undertaking, which is now the new Artemis missions. So now going a bit further, this is Argonaut, which is our truck, as you may call it, which is a big spacecraft that brings volume and mass to the moon. In fact, what you see here in this golden color is this Argonaut spacecraft. It can bring about 1.5 tons of mass to the moon, which can be equipment, experiments, can be power generators, whatever you will need on Mars in order to really establish a moon base and therefore infrastructure and start living and building up some presence on the moon. And this will be reality, I would say, in the middle of the next decade, because now first we have to go back to the moon on the surface to explore, but then really establish infrastructure. And this Argonaut launch, which we have just decided in November last year, will be launched at the end of of this decade, so around 2030, 2031, and will then bring this mass to the moon and really establish, as you see here, in this futuristic scenario. Something else that comes back to our planet is secure connectivity. Of course, you all know very well about Starlink. So Europe is also engaging in something similar. Of course, we are a little bit behind, if I may say so, in order to establish such a network of broadband internet. But we have agreed and decided on the funding. Again, this is European Commission together with European Space Agency in Europe to build up a constellation of secure connectivity, broadband internet for hard government services, light government services, and commercial uses. So this is just in the making, and certainly something that is extremely important also for security. We have seen the importance of communication also in the war of Ukraine, and this is something that, of course, I don't need to explain how important this independence is. Another example which is shown here is quite unique, will be the first one, which is a satellite, as you see here, that is grabbing a space debris, some space junk. This is, in this case, an upper stage of a Vega launcher, which is floating in orbit. It is disturbing, and you see here some numbers of how many objects of space debris, space junk, as you may call it, are floating around, of course, in different sizes. But the small ones are actually also quite dangerous because they are like a bullet, and if they hit a spacecraft or even the space station, this is certainly can cause major damage. So what this will do, Clear Space 1, is this spacecraft really grab this piece of metal or this upper stage of Vega and bring it out of the orbit and remove literally space junk from this orbit. Of course, you may say removing one doesn't solve the problem, but in my opinion, there is more and more to come, and this is one of the first ones, if not the first one, that is doing it in this way. And I'm very glad to see this launched in 2 to 3 years from now, at the end of 2025. It's actually made in Switzerland. It's European Space Agency who is funding it, but the main contractor is actually here in Switzerland, together with some other companies in Europe, and really showing how this can be done. And I think this is more and more needed. We want to establish a zero debris policy, which means that if you bring a spacecraft into orbit, you have to remove it. This policy should be in place in a couple of years. I'm working now with my government in Europe, and hopefully this will be adopted universally, because we need to protect our orbits for our own safety and the safety of spacecraft and astronauts. Let me show you one last example before we go back to a bit more interactive discussion. This is Solaris. Solaris is something quite amazing, and I have to really put a small caveat into this example. So what it does, it is a study, a feasibility study, where we want to investigate whether you can collect solar power in space in a large scale. Of course, you can do it already. Every satellite has a solar panel and is using solar energy in space. But what we are proposing here is to really have a big structure, which will be a few kilometers wide or long in dimension, a few thousands of tons heavy, so just to give an impression of the dimensions, that could produce electric power in the order of gigawatts, and these gigawatts then beaming down to the surface and then collecting them, of course, at the surface and then using them for electricity, for energy as we need them. So this is the theory. The theory itself is actually old. It does exist since many years. In a small scale, we are doing power transmission every single day with satellites in microwaves, but at a much smaller scale, at the order of kilowatts and a few hundreds of kilometers. But this is really big scale, thousands of kilometers and gigawatts, and this is something that we're investigating right now. So what we have done, I've got a funding of 60 million from the member states just last November to really do a feasibility technically, whether this is possible, because as you can imagine, such a structure needs to be assembled in orbit with in-orbit robots who are doing this work. You have to stabilize the structure, that it's not moving away and staying on the position, and of course testing technology of power transmission from a geostationary orbit all the way down to the surface with all the complications you can imagine, and this is the feasibility we are doing from a technology point of view. Of course, there's also an economic viability which we have to test. Is it worth doing it in space rather than down on the surface? We do not have the firm answer yet. There are some models and calculations, but with a very big error bar, and that's what we want to do, to reduce this error bar, to know what it means in terms of cost in order to really implement such a project. It's very futuristic, but the order of magnitude is quite significant. And if it works, and I really put a big if in the room here, if it works, it would be a huge improvement for climate change, but also energy autonomy, because I don't need to explain how dependent we are in today's energy crisis from other sources, but also climate change, of course, is a huge issue, and this could really solve two of these problems at once, if it works at a large scale, but this we will find out in 2 to 3 years, and then I could come with a major proposal. Let me stop here in terms of inspiring you and launching the debate, just coming back to this inspiring image of the James Webb Space Telescope, and hand back to Dava.
Thank you. Thank you. Thank you both. Thank you so much for the inspiring words. So again, starting out close to Earth, low Earth orbit on the International Space Station, we are living off planet. Matthias is living off planet and humanity will continue to live off planet. We will become an interplanetary species, going to the moon to stay this time, to buy down our technologies in preparation of that human mission and exploration of Mars. Why Mars? Simply in exploration, I think we have 3 fundamental questions. Are we alone in the universe? Are there other habitable planets? And what about life? And when will we find it? Past life, or current life? We have the chemistry, we have the building blocks of life in our exoplanets and on Mars. Sulfur, hydrogen, the building blocks, the chemistry that life would like to exist. So it's an amazing future. It makes us as technologists dream big, make sure that our technology can go to these amazing places. And hopefully you also heard coming back to home. What are the benefits of exploration for humanity in terms of power, in terms of also the biomedical applications, in terms of we always have to be thinking about climate. And we observe the overview effect. All astronauts look down on Earth and think of spaceship Earth. They think of humanity together. They don't think of which nation they're from. They think of everyone together. We all are astronauts. We've lived through the pandemic. You've been in isolated confinement. And so you're all astronauts. Welcome to the club. You know how it's like to be an astronaut, and we know that we're better together for some of these huge challenges. So we're going to open it up for your questions. What's on your mind? What do you want to ask about the future of exploration? Please, we're handing around a mic, and here it is. Maybe introduce yourself real quickly, and then your question.
I'm Siddharth Jain from India. Question about going to Mars. Is there any way to shorten the time period, or is there any technology coming up which will increase the speed of the craft and reduce the time from 6 months to any shorter period of time? Any new engines coming up for that?
I mean, this is a big question which is on the mind of major space agencies. I know that NASA is doing a lot of research in this direction as well, also we at the ESA side. Today, it does take 6 to 8 months to go there. This is the reality, and you can imagine for astronauts like Matthias and his colleagues to be 6 to 8 months confined in a space capsule, to go there and then stay there for a while and again 6 to 8 months back is a long mission and also dangerous, if I may say so. So of course we want to reduce that. Today there is no proven technology on the table, but I can tell you that we are working, we means NASA, ESA, other space agencies, a lot, very intensely to shorten this time significantly. Of course, nuclear propulsion is one of these sources that might do the trick, but there are a number of questions attached to it. So yes, we're working on it, but not yet ready.
Yeah, but hopefully in the next, like you said, hopefully in the next decade, because we'd love to shorten the trip to half. You know, wouldn't it be fantastic if we could go in 3 to 4 months? And so NASA, I was a former NASA deputy administrator in the Obama administration, and so placing those research and development, you know, putting it into science, research and development, so that in the next decade, when we get to Mars with humanity in the 2030s, then maybe that's a possibility. But right now, we have heavy lift launch. Fantastic. The Artemis, that's step 1. Get back to heavy lift launch capability, which we now have, again, after 50 years for getting to the moon next, and then Mars beyond that.
Hi, Kimberly Washington, founder of Space for Girls, and also Executive Vice President and Equity Partner of Deep Space Biology. We've worked with NASA for the past 2 years. And my question is about human health. All of the ambitious goals that all of the different space agencies are aiming for to put humans on the moon, humans on Mars, What is ESA doing to accelerate the protection of human health, radiation exposure, all of the other factors? And what types of technologies are you integrating to scale this level of protection and knowledge?
No, thank you. We have a program, but I think the best one really to respond to that is the one who has been in space and exposed to the dangers you mentioned. Matthias, you may want to comment.
Yes, so like on the International Space Station, we get approximately a daily dose of 1 millisievert. On the moon, it will be roughly 6 times higher. So like a 6 months mission to the ISS is roughly equivalent to 1 month's mission to the moon. Flying to Mars and staying 2 to 3 years on the road, or in space I should say, would exceed the limits that we currently allow for our astronauts. So definitely there is this need to improve the shielding, the protection against radiation. There are the classical means. You can bring a lot of lead and build a wall of a meter or 2 of lead around you, but then your spacecraft would never fly. So we need to come to more smarter and new solutions. And Dava, I hand it back to you because you are working on smart new materials.
Yeah, so some of the research and development for radiation protection for deep space missions, the moon and Mars, we have to protect the astronauts from the radiation. And now it's cosmic galactic rays as well as the solar particles. But there is promising new technologies, polyethylene, some carbon fibers, some boron nano's. So we're looking at new materials in development to help protect astronauts as well as our electronics and the spacecraft. So we'll be able to test those out on the moon, hopefully. So we'll know more answers, before we send the astronauts to Mars. I would also like to mention muscle and bones, because not everyone might be familiar. That's why the International Space Station is an incredible laboratory. So Matthias is exercising a couple hours of days, because you go through about 30% muscle atrophy. That's okay, you can exercise and come back to Earth. He's doing well. Bone loss, we might lose 1 to 2% bone mineral density per month. Now who wants to sign up for the 4-year Mars mission? So, but it's that's an accelerated process. You might lose 1% bone mineral density, but when you're 50 to 60 years old. On the space station, it's a 10 times factor, but we have countermeasures. And why is that so important? Just for our astronauts, for all of us living on space, to think about osteoporosis, what are the biomarkers. So all of the biomedical work to keep our astronauts healthy and well really have enormous Earth applications in terms of the pharmaceuticals and the countermeasures that we undergo.
Yeah, and the side effect is like if you have a bone degradation, this bone degradation leads to the formation of kidney stones. And kidney stones is an absolute killer for a spaceflight mission. When we have a kidney stone patient in space, we would bring back the entire crew. So imagine you fly to Mars, you wouldn't bring somebody back. How do you treat a kidney stone on a mission to Mars? So you see there's lots to learn.
Hi, I'm Nimrod. We've seen a strong and significant shift in the balance between private and public initiatives in space recently. Here on Earth, it took us a lot of time to find the right balance in public-private initiatives and to understand who should do what. And I wanted to ask, what's your take on that? Looking to the future in space exploration, who should do what?
Yeah. No, that's a fantastic question, and there's a huge revolution ongoing right now. I mean, triggered also thanks to NASA through the CCP, the Commercial Crew Program and the Commercial Cargo Program. And this is also happening in Europe. I have actually, since I'm Director General of ESA since a bit less than 2 years now, I've put one of the priorities of my strategy in my post to foster commercialization. And this really means that we, as public entity, as the European Space Agency, act much more as a customer, as an anchor customer or first customer of space technology that is being developed, whether this is a commercial space station, or this is a rocket, or this is a satellite. So we much more act as a customer rather than developing everything from scratch. Having said that, of course, and this will remain our core responsibility, we will keep developing technology either as building blocks, an engine for a rocket or some elements, but together with industry. And the approach will much more be one of co-engineering together with industry, where industry takes responsibility as the application matures. So yes, there's a huge revolution ongoing in the US, also in Europe, and this is something that will change space drastically in the next decade. And actually, that's quite good. That's quite exciting, because that really brings it much more into the private domain, in the commercial domain, and this is what really drives it forward.
Yeah, our public-private partnerships, like I mentioned when we laid them out for NASA, the government has a huge role to play in all space agencies to exploration, to get us beyond. But when it makes business sense, let's have the private sector do that. Governments aren't great at that. So in terms of the operations, let's have the private folks. So we've seen disruptive innovation, not so much in the technology, but in the launch frequency, in the capabilities. And that's what the governments are betting on. Let's see that disruption in the business model, the organizational change, so can we move forward. So it really is teaming between governments, industry, and I would add academia as well for the future. And those partnerships are really important. And the last decades kind of laid the groundwork for this. Very exciting for the real democratization and access to space. We are out of time, but I want to thank again our panelists for such an inspiring talk.
Thank you. Thank you.
Thank you.
Thank you.
And to you, the audience, so exploration is back and thriving is the final message to leave you all with, and you all need to be a part of it, and you're all welcome.
Thank you.